Welcome to my channel. In this video, we are going to discuss about the multiple choice question and answer from the antenna and microwave engineering from the unit 1. So already we discussed in the previous video the basics of antenna. We discussed some of the questions. So in this video, we are going to discuss about the antenna parameters. Okay, some of the antenna parameters we will discuss in this video. So the first one, dash is independent of distance. Pointing vector, radiation intensity, both A and B and none. So radiation intensity. Radiation intensity, it is independent of distance. Next one, power radiated from an antenna per unit solid angle is called radiation intensity. It's a true or false. It's a true only. The radiation intensity, it is nothing but what is the definition of radiation intensity means? It's a power radiated from an antenna per unit solid angle. Okay. So how much power radiated per unit solid angle? It is mentioned by the unit. It is called as a radiation intensity. Then the next one, power per unit area is termed as Poynting vector. Okay, it's a true or false? True. Okay, power per unit area, it is called as a Poynting vector. And radiation intensity means power radiated per unit solid angle. It is called as a radiation intensity. Power per unit area, it is termed as a Poynting vector. The next one, steradian is a measurement unit of dash. Point angle, linear angle, plane angle, solid angle. Solid angle. Steradian, it's a measurement of solid angle. Okay. Then the next one, according to the geometry, how many steradians are present in a full sphere? So in a complete sphere, how many steradians are present means 4 pi steradians are available. Okay, in a full sphere, 4 pi steradians are available. Then 1 steradian is equal to dash square degrees. Okay, so 1 steradian, it is nothing but how many square degrees? 360, 180, 3283, 41, 253. So 3283. That is, this is actually 3282 point something. So that is round off to 3283. 1 steradian is nothing but 3283 square degrees. Next one, radian. Radian is a measurement of dash. Steradian, so previously, that is this question you see, steradian is a measurement of solid angle. Similarly, the radian is a measurement of plane angle. Okay, then the different parts of radiation pattern are referred to as loops or planes. Loops. Okay, so the different parts of radiation pattern, it is called as a loops. The main loop, side loop, back loop. Okay, so the different parts of radiation pattern, we are calling it as a loops. The next one, the radiation loop containing the direction of maximum radiation is called as minor loop, side loop, back loop, major loop, major loop. So the radiation loop that contains the direction of maximum radiation. So for example, if the radiation pattern is like this means, so this one is, this is indicating the direction of maximum radiation. So this loop, we are calling it as a major loop or main beam. Okay, that is also another name. All the loops except the major loop are called minor loop. It's a true or false? True. Okay, so except this major loop, the remaining all this small side loop, this all remaining loop, it is called as a minor loop. Yes, the largest minor loop is called as dash. Okay, so in this major loop, so nearer to this major loop, there is a two largest minor loop is available. That largest minor loop, it is called as a side loop. Okay, so this two thing, we are calling it as a side loop. So side loop is nothing but the largest minor loop is called as a side loop. Then the next one, in a non-isotropic directional antenna, which radiating loop axis makes an angle of 180 degree with respect to major beam of an antenna. It's a minor loop, side loop, back loop, none of the above, back loop. Okay, so what's the meaning means? So if it is a major loop means, for this major loop, the 180-degree opposite. So 180-degree opposite, here we will get one minimum amount of radiation. This is said to be the back loop. Okay, so in a non-isotropic radiation directional antenna, which radiating loop axis makes an angle 180-degree with respect to major beam of an antenna, it is called as a back loop. Then the next question, dash is also called as 3 dB beam width. That is FNBW. FNBW means first null beam width. Okay. HPBW, half power beam width. Both A and B, none of the above. So dash is also called as a 3 dB beam width, means the half power beam width. HPBW, the half power beam width, we are calling it as a 3 dB beam width. Next, the beam width of antenna pattern measured at a half power point, it is called as a half power beam width. Okay, so the beam width of antenna pattern measured at half power point. That is, you just see, this is the major loop, means from this, if this maximum radiation, it's a 1 means, so we have to reduce the half power point. Okay, so if it is a power pattern, this is the maximum power, means this is the 0.5. Okay, so in which 2 point the power reduces to half of the point, it is called as a half power point. So the angular measurement between these two half power point, it is called as a beam width. Okay, so this beam width, we are calling it as a half power beam width. HPBW, beam width of the antenna, it's a measure at half of the maximum power received by an antenna, or this half power beam width, it is also called as 3 dB beam width or half null beam width. Okay, then the next one, which among the following defines the angular distance between the 2 points on each side of the major loop, especially when the radiation drops to 0. Okay, so that is a half power beam width, first null beam width, side loop level, front to back ratio. So what is the question means here? The angular distance between the 2 points on each side of the major loop, especially when the radiation drops to 0. Okay, so here that is here they are saying it as, if it is a major loop means, so this major loop, it's dropped 0 at this point. Okay, so the angular distance between these 2 points, we are calling it as a this thing. Okay, so the angular distance between this two null, it is called as a first null beam width. So the angular distance between the 2 points on each side of the major loop, especially when the radiation drops to 0. So the radiation drops to 0, it is called as a null. Okay, so that's why this angular width, it is called as a first null beam width, FNBW or BWFN. Next one, at which angle does the front to back ratio specify an antenna gain? Okay, at which angle does the front to back ratio specify an antenna gain? So it's a 0 degree as well as 180 degree. Okay, so in 0 degree we will get the maximum radiation, in 180 degree we will get the back loop. So front to back ratio, it is 0 degree and 180 degree. Then the next one, the antenna has a field pattern of E of theta equal to cos squared theta, where the theta varies from 0 degree to 90 degree. Half power beam width of antenna is dash. Okay, 33 degree, 66 degree, 1200 degree, none of the above. Okay, so 66 degree is the answer. So how to solve this problem means, first one, the half power beam width, you know the definition. The half power beam width of antenna is obtained by equating the field pattern of the antenna to 0.707. That is 0.707 is nothing but 1 by root 2. So we have to equate this E of theta equal to cos squared theta to 0.707, and we have to calculate the value of theta. Okay, then the twice the theta, it is nothing but a half power beam width. Okay, so you see this is the given problem. So this question is a very important 2 mark question. Okay, So this question is already asked in December 2017 and 2 more years also. Okay, so you see, in order to solve this problem, first this electric field E of theta equal to cos squared theta. Okay, this electric field pattern cos squared theta, we have to equate it to 0.707. Okay, why we have to equate it to 0.707 means at a half power point, the electric field reaches the value of 1 by root 2. So the 1 by root 2, we are calling it as a 0.702. Okay, so that's why in order to calculate this theta, the electric field value, we have to equate to 0.707. So cos squared theta is equal to 0.707. So you take square root on both sides. So cos theta equal to square root of 0.707. So from this, if you are calculating the theta, cos inverse of square root of 0.707, it's a 33 degree. Okay, so this one is nothing but half of the angle. So as per our half power beamwidth definition, the half power beamwidth definition, it is a beamwidth between the two half power point. Okay, this is a one half power point. That is, now we are calculating the angle from this center point to this one. Okay, similarly the same theta angle we will get this right side also. So the total half power beamwidth is nothing but theta plus theta, it's a 2 theta. So that's why the half power beamwidth, it is equal to 2 theta. So 2 into 33 degree, it's a 66 degree. It is the answer. So the answer is 66 degree. Okay. Then the next question. So you see, this is the one. The next one, the antenna has a field pattern of E of theta equal to cos theta cos 2 theta. The first null beam width of the antenna is, okay, the first null beam width of antenna, we have to calculate it similarly. So you see, here the E of theta equal to cos theta cos 2 theta. So the question is that here we have to find out the first null beam width, the relation between the first null beam width. Okay, so in order to calculate this first null beam width, so the E of theta, you know, the first null beam width, it is nothing but the electric field value, it reaches 0. Okay, at an angle, the electric, that the first null, the electric field value, it reaches the 0 value. So the E of theta value, we have to equate it to 0. So what is the E of theta value? Cos theta cos 2 theta. So the cos theta cos 2 theta, we have to equate it to 0. So in which condition, for which angle of this theta, this cos theta cos 2 theta, it reaches 0 means it's a 45 degree. Okay, so the theta value we calculated. Then from this, the first null beam width, what is mean by first null beam width? The angular width between the two first null, okay, in left side and right side. So that is, we calculated one angle, one half angle from this null to center point. Similarly, this is also another one theta. So the 2 theta, it is nothing but a first null beam width. So the first null beam width is equal to 90 degree. Okay, this is the first null beam width. That is for half power point. Okay, for half power point calculation, we have to equate the E of theta value. We have to equate it to 0.707. We have to find out the value of theta. And if you are twicing that theta means that is said to be the half power beam width. Okay, if we want to calculate a beam width between the first null, we have to equate the E of theta value to 0. Okay, the electric field, we have to equate it to 0, and we have to find out the value for theta. Then if we are twising this theta value, we will get the bandwidth between the first null. Okay, FNBW. So it's a 90 degree. So the 90 degree is the answer. Okay, then the next question, the solid area through which all the power radiated by the antenna is dash. It's a beam area, effective area, aperture area, beam efficiency, beam area. The solid area through which all power radiated by the antenna is called as a beam area. Okay, then next question, as the beam area of antenna decreases, the directivity of the antenna increases, decreases, remain unchanged, depends on the type of antenna. Increases. Okay, why increases means, so you know the relation between the beam area and the directivity. So this is the relation between the directivity and the beam area. So the formula is that the directivity D is equal to 4 pi divided by the omega A. So where D is a directivity, this omega A is called as a beam area. So from this relation, we can say that the directivity and the beam area is inversely proportional. Okay, so that's why if the beam area decreases means the directivity of the antenna increases. Okay, increases. Then the next question, beam width and directivity are both measures of focusing the ability of the antenna. It's a true or false? True. Okay, so in order to measure the ability of the antenna, beam width and directivity, both the thing, it's a important measurement units. Okay, the next one, if the antenna radiates over a half sphere, the directivity of the antenna is, okay, so if the antenna radiates a half of the sphere, okay, so half of the sphere means what is the directivity of the antenna? So already you know the formula, the directivity, it is nothing but 4 pi divided by the beam area. Okay, so here they are mentioning it as the antenna radiates over a half sphere. So half sphere means the area of the half sphere, it is nothing but a 2 pi. So the beam area of the antenna is 2 pi. So that's why the directivity D is equal to 4 pi divided by 2 pi. So 2. Okay. So if the antenna radiates over a half a sphere, the directivity of the antenna is 2. D value equal to 2. Okay. Then the next question. The minimum value of directivity of an antenna is dash. Unity, 0, infinite, none. Unity, that is 1. The minimum value of directivity, it is equal to 1. Next question. The directivity is inversely proportional to half power beam width between the first null, beam area, and beam width, beam area. Okay, so you know the directivity and the beam area, this two things is inversely proportional according to this relation, D equal to 4 pi by omega A. This is a beam area. So the beam area and the directivity, this two things is inversely proportional. The next one, the gain is always dash than directivity. The gain of the antenna. Okay, so the gain, there are so many parameters of antenna is that antenna gain, antenna directivity, beam width, bandwidth, and so on. So the antenna gain is always dash than directivity. It greater, lesser, equal, none. Okay, lesser. The gain is always lesser than the directivity. Okay, the G value is always lesser than directivity. Since the gain formula is that the gain K is equal to the efficiency K into D. Okay, this is the formula. So that's why the gain is always less than the directivity. The next one, directivity and resolution or dash. Okay, directivity and resolution of the antenna are different, same, both A and B, none of the above, same. Directivity of the antenna and resolution of the antenna is same only. The next one, if an antenna has a directivity of 16 and a radiation efficiency of 0.9, then the gain of the antenna is dash. Okay. So what is the relation between the directivity and the radiation efficiency means? So the product of directivity and efficiency, it gives the gain of the antenna. Okay. So if you are multiplying this directivity and efficiency, we will get the gain. Okay. That is, you see, the gain G is equal to efficiency into this efficiency. Sometimes it is called as eta. So gain is equal to eta into D, efficiency of the antenna into directivity. So the product of efficiency and the gain, you just multiply these two things. That is, you see, the directivity 16, radiation efficiency 0.9, you just multiply. So we will get, the answer is that 16.2. Okay. Then the next one, what does the beam width of antenna tell us? Okay, so the beam width of antenna tell us signal strength, signal power, directivity, degradation. So from the beam width, okay, so if that is for one antenna, they are telling us the beam width of this antenna is this much. Okay, so from the beam width, so what are the thing we know means it's a signal strength, it's a signal power, directivity, degradation, directivity. So from the beam width, we can calculate the directivity of the antenna. So the measure of antenna directivity is a beam width or angle of radiation pattern over which the transmitter energy is directed or received. Okay, so the beam width is also one of the important parameter in an antenna radiation pattern. So from the beam width, we can calculate the directivity. Then the next question, if the power input to an antenna is 100 milliwatts, the power input, okay, for one antenna, we are applying the power input as 100 milliwatts. And if the radiated power measured is 90 milliwatt, then the efficiency of the antenna is dash. Okay, so the antenna efficiency, it is defined as it's a ratio of radiated power to the input power. Okay, so power radiated by the particular antenna divided by input power, it is called as the antenna efficiency. So the radiated power is 90 milliwatt divided by the antenna input power is 100 milliwatt. So 90 divided by 100 milliwatt. If you want to mention in terms of percentage, means we will get the answer as a 90%. Okay, so 90% is the answer. Then the next one, the ratio of gain to the directivity, it is also called as antenna efficiency factor. It's a true or false? True. Okay, so the ratio of gain to the directivity, it is called as an antenna efficiency factor, K. Okay, so this is the relation between gain, efficiency and directivity. Okay, so these are all the some of the questions about the antenna parameters. Okay, so thanks for watching my video. In the next video, we will discuss remaining parameters of the antenna. Okay, so thanks for watching. So if you want to learn the previous video, means I will give the link for those video in the description box, and iCode also you can refer it. Okay, so thanks for watching my channel. Keep watching. Thank you.